The idea that black holes could produce high-energy particles was once considered impossible. If particles collide near the event horizon, they could reach near unlimited energy. But there was a problem. They should have been lost forever, until new models revealed something unexpected. Some of them escape, and once free, they travel across the universe as cosmic rays. So the question is, what have we actually found? From Earth, the night sky appears ethereal, almost peaceful. It feels so distant from human civilization that you might assume we're completely untouched by whatever is happening out there. But that couldn't be further from the truth. We are under attack. Cosmic rays are constantly striking our planet from every direction. Tiny, invisible particles colliding with the atmosphere and triggering cascading chains of ionization that can disrupt satellites and damage sensitive electronics. But where do they come from? For over a century, astrophysicists have searched for their origin, and for most of that time, the universe refused to answer. Even the nature of the source remained hidden. But now, a new wave of research is finally beginning to uncover the truth. Not only are we starting to understand what to look for, we are realizing these sources are far more powerful than we ever imagined. What in the universe could possibly generate a quadrillion electron volts of energy? If you're curious about the hidden forces shaping our universe, consider subscribing, because what we're about to uncover goes far beyond anything we expected. In this journey, we'll follow the trail of cosmic rays all the way to the very edge of known physics. We'll explore how scientists detect the most energetic particles ever observed, and encounter a completely new class of cosmic objects, entities so extreme that until recently, they belonged more to science fiction than reality. The Milky Way is filled with energy, but our eyes can only detect a tiny fraction of it. Beyond visible light, charged particles release far more powerful radiation in the form of X-rays and gamma rays, scattering energetic fingerprints across space. By decoding these signals, astronomers can trace how energy moves through our galaxy. But among all these particles, there is one group that still refuses to reveal its origin. In 1912, Austrian physicist Victor Hess carried out a daring experiment. He ascended to an altitude of over 17,000 feet in a balloon, measuring how quickly atoms in the upper atmosphere became ionized. Based on existing theories, the rate should have decreased with height. Instead, it tripled. At that moment, Hess realized something profound. The radiation he had been studying did not come from Earth at all. It was arriving from space. He had discovered cosmic rays, and they did not come in peace. Earth is constantly bombarded by them. These high-energy particles, mostly protons, travel at nearly the speed of light and slam into the atmosphere, creating cascades of secondary particles that rain down to the surface. Some of these particles pass harmlessly through us. Others can alter DNA, damage cells, and increase the risk of mutation. When they strike satellites, they can trigger bursts of ionization that degrade circuits or cause sudden system failures. This is not a distant phenomenon. It is happening above us, every second. And cosmic rays are not just a nuisance to our technology. They have challenged our understanding of the universe itself. For over a century, one question has remained unsolved. Where do they actually come from? Their behavior makes them almost impossible to trace. Magnetic fields twist their paths across space, and by the time they reach Earth, they have already shattered into cascades of secondary particles, erasing any clear signature of their origin. This problem becomes obvious when scientists try to map the cosmic ray spectrum, plotting how many particles arrive at different energy levels. What they found was unexpected. At a certain energy level, the curve suddenly bends, a sharp drop, known as the knee, Beyond this point, particles with extremely high energies, above 4 peta-electron volts, become dramatically rarer. For a long time, scientists believed this marked a boundary, separating particles born within our galaxy from those arriving from beyond it. Others were not convinced, and just as the mystery seemed impossible to solve, a new observatory changed everything. Before we go further, take a moment to consider this. If these particles are this rare and this energetic, what kind of cosmic engine could possibly create them? Now, it is time to look at the observatory that brought us closer than ever to the answer. High in the mountains of Sichuan, at an altitude of nearly 15,000 feet, sits one of the most advanced detectors ever built. The Large High Altitude Air Shower Observatory, known as LHAASO, was designed with a single purpose: to capture the highest energy particles in the universe and finally trace them back to their source. To measure the knee of the cosmic ray spectrum, you need two things: a detector large enough to capture these rare events, and the ability to identify the original particle from the cascade it creates. And that is the real challenge. The higher the energy, the rarer the particle. For the most extreme cosmic rays, fewer than 1 particle per square kilometer per century reaches Earth. To catch them, you need something far larger. That is why LHAASO spans an area equivalent to nearly 200 football fields, turning an entire landscape into a detector. When a cosmic ray strikes the atmosphere, it creates a cascade of secondary particles. What scientists see is not the original particle, but the debris it leaves behind. From this chaotic shower, they must reconstruct the identity of the source, determining whether it was a proton, a helium nucleus, or something even heavier. It is like solving a puzzle where most of the pieces vanish before you can examine them. LHAASO is uniquely equipped for this task. Its network of interconnected detectors captures different aspects of the particle shower, allowing scientists to reconstruct the event with unprecedented detail. And even before the observatory was fully completed, it delivered something unexpected. Within months of operation, it began detecting an extraordinary number of gamma rays. By 2021, LHAASO had detected gamma-ray photons with energies exceeding 1 peta-electron volt, and one reaching 1.4 peta-electron volts, the highest energy photon ever recorded. To understand how extreme that is, consider this. It is nearly 150 times more energetic than the most powerful particles produced by the Large Hadron Collider, a single particle carrying an amount of energy that pushes the limits of what physics can explain. An energy like that does not appear without a cause. It must come from something. For decades, scientists had predicted the existence of such sources, but now, for the first time, they had proof. These cosmic engines had a name: PeVatrons. A PeVatron is any object capable of accelerating particles to peta-electron volt energies, and finding them would change everything. But there was one key advantage: gamma rays. Unlike charged particles, travel in straight lines. They are not deflected by magnetic fields. That means they point directly back to their source. By mapping these signals across the sky, scientists identified 12 distinct regions capable of producing ultra-high energy gamma rays, several of which showed clear signs of accelerating particles to extraordinary energies. There was one problem. LHAASO could see the direction of these gamma rays, but not their distance. 12 lines stretching endlessly into space is not a precise map, but there was a crucial clue. Since the beginning of the universe, space has been filled with low-energy photons left over from the Big Bang. When ultra-high energy gamma rays collide with these background photons, they disappear. This changes everything. It means gamma rays cannot travel across the entire universe. If LHAASO is detecting them here on Earth, then their sources must be relatively close, not in distant galaxies, but inside our own. Suddenly, the search space collapsed from the vast universe down to the Milky Way, and the race to find their origins truly began. Long before LHAASO, scientists had already proposed possible sources. Space is filled with extreme objects, but which of them could generate such enormous energies for decades? One leading theory pointed to supernova remnants. When a massive star explodes, it releases an immense amount of energy, enough that even a small fraction could power the cosmic rays we observe. When a star explodes as a supernova, it sends a powerful shockwave into space. At this boundary, particles are repeatedly scattered back and forth, gaining energy with each pass. Over time, some can reach extreme energies, but there is a limit. This process is only efficient during the earliest phase of the explosion, a brief window of roughly 100 years. After that, the system fades. There is, however, a workaround. Some particles may escape the supernova remnant and become trapped in nearby dense clouds of gas. There, they can collide with matter and produce gamma rays with energies reaching 1 quadrillion electron volts, even long after the original explosion has faded. This means supernova remnants can still contribute, but they may not be the full answer. Another candidate is even more extreme: pulsars. These are rapidly rotating neutron stars, formed in supernova explosions, with magnetic fields billions of times stronger than Earth's. As they spin, they generate powerful electric fields that rip particles from their surface and launch them outward in a high-speed wind. When this particle wind collides with surrounding gas or dust, it suddenly slows down, forming a shock boundary. At this point, particles are accelerated to even higher energies. The LHAASO team estimates that more than 30% of the candidate PeVatrons they detected could be linked to pulsars. But even this may not be the most extreme source in the universe. The final category of cosmic ray sources came as a surprise. When scientists looked closer at the cosmic ray spectrum, the knee was not smooth. There was a bump, an anomaly. The data did not match anything known. Not supernova remnants, not pulsars, which meant something else was at work, something more extreme. To explain it, scientists had to look beyond conventional models and consider a possibility that once seemed almost too radical. Nature's most powerful accelerators, black holes. Near a black hole, the rules begin to break down. Space and time themselves are distorted. And in that warped environment, particles do not simply collide. They collide inside a gravitational field pushed to its limits. According to theoretical models, when two particles fall toward a black hole and collide near the event horizon, their energy can rise to extraordinary levels, effectively unbounded under the right conditions. For a long time, this idea was dismissed. Any particle reaching that region would simply be swallowed. But newer models changed the picture. Not everything falls in. A fraction of these particles can escape, launched back into space with energies that should not exist under normal conditions. And once they are free, they travel across the galaxy as cosmic rays. So what have we actually found? Despite all this theory, identifying real sources remains incredibly difficult. The LHAASO has detected multiple candidates, but tracing each signal back to a specific object is another challenge entirely. Still, progress is being made, and among the first confirmed sources is something we have known for centuries, but never truly understood. The Crab Nebula, located about 6,500 light-years away. The Crab Nebula is the remnant of a stellar explosion, but it is far more than a beautiful cloud of gas. Inside it, Particles are being accelerated to energies reaching 1 quadrillion electron volts. Electrons moving with energies far beyond anything humanity has ever created, revealing that even familiar objects can hide extreme physics. And this is only the beginning. Messier 1 is one of the most studied objects in the universe, and it offers a rare window into how nature builds its own particle accelerators. In gamma rays, it behaves in a highly dynamic way, producing intense flares that can last from a few hours to several days. These flares are not random. They are signatures of electrons being pushed to extreme energies. Exactly how this happens is still debated. It could involve shock acceleration at the boundary of the pulsar wind, magnetic field lines snapping and reconnecting, or more complex processes within the particle flow itself. When electrons reach such energies, they transfer part of that energy to background photons, boosting them into gamma rays that we can detect. But accelerating electrons to this level is extremely difficult. They lose energy almost instantly. To produce gamma rays at 1 quadrillion electron volts, the electrons themselves must have carried several times that energy. This confirms that Messier 1 is a true PeVatron. And even then, this is only part of the story. Messier 1 is what scientists call a leptonic accelerator, meaning it primarily accelerates electrons. But cosmic rays are mostly protons. So the real targets are hadronic accelerators, objects capable of pushing protons to extreme energies. And that is where the search becomes even more intense. The most energetic photon ever detected, at 1.4 peta electron volts, pointed scientists toward a new region of interest. The constellation Cygnus. Stretching across a vast area of the sky, this region contains some of the most active star-forming environments in our galaxy. Inside it lies the Cygnus cocoon, a massive bubble of energized gas surrounding a dense cluster of young stars. These young stars generate powerful stellar winds, streams of particles moving at incredible speeds, capable of accelerating other particles to extreme energies. And the alignment between this region and the gamma rays detected by HASO made it a strong candidate. But there was a problem. Too many possible sources, too many energetic systems in the same direction. Among them was Cygnus X-3, a system consisting of a massive star and a compact object, likely a black hole or neutron star. The massive star feeds material into its companion through intense stellar winds, while the compact object launches powerful jets of plasma. Together, they form a natural particle accelerator on a scale we can barely comprehend. At first, it was impossible to tell which object was responsible. But then scientists noticed something unusual, a repeating pattern, every 4.8 hours. The signal returned, not just in gamma rays, but across multiple wavelengths, a cosmic rhythm, a heartbeat hidden in the data. That pattern revealed the truth. Every 4.8 hours. The compact object in Cygnus X-3 completes an orbit around its massive companion. In that moment, the source was identified. The gamma rays were coming from Cygnus X-3, another PeVatron, confirmed. Cygnus X-3 turned out to be even more extreme than expected. The highest energy photons detected from this system reached 3.7 peta electron volts. And because these photons are produced by accelerated protons, the protons themselves must carry several times more energy. This places Cygnus X-3 in a completely different category. Not just a PeVatron, but a super PeVatron, capable of pushing particles to at least 10 peta electron volts. And this raises a deeper question. If objects like this already exist in our galaxy, what else have we not yet found? What once seemed like a search for a handful of rare objects has quickly expanded into something much larger. The first catalog of galactic PeVatrons listed 43 sources. Just a few years later, that number has grown to more than 75. and each one represents an extreme environment where the laws of physics are being pushed to their limits. This forces us to rethink something fundamental. We once imagined the Milky Way as a relatively calm and stable place, but that picture is no longer accurate. Our galaxy is filled with hidden engines, accelerating particles to energies far beyond anything humanity can create. And every second, a small fraction of that energy reaches us. The search is far from over. Observatories around the world are now working together, combining data across different wavelengths to build a complete picture of these phenomena. With each new observation, we move closer to understanding how the most powerful accelerators in the universe actually work. But the deeper we look, the more unsettling the picture becomes. Because if our galaxy alone contains dozens of these extreme sources, then the universe beyond must be filled with them. And that brings us back to where we started. We are not isolated. We are not untouched. Every moment, we are being reached by signals from the most violent environments in existence. The question is no longer whether they exist. The question is how far they can go. If this changed how you see the universe, consider subscribing, because this is only the beginning of what we are starting to uncover.